So where does the Van Hoff factor come from? Well, it comes from a concept called colligative properties. And colligative properties, which, in case you can't tell, that's what the lab was all about, come in lots of different shapes and sizes. There are lots of different colligative properties. But a colligative property so you don't have to write colligative properties all over again. That's a really long term, right? But a colligative property is something that changes based on the amount and type of solute added. Oops. So colligative properties are things where if I take something, I add a little bit of solute to it, I add something, dissolve that solute into it, it's going to change that property. Examples of this, there are so many examples of this. Conductivity is one. Density is another one. Flavor, believe it or not, many chemists consider flavor to be a colligative property. Saltiness, right? How salty something is, how sweet something is, how much sugar you put in there, right? All of those things are colligative properties. Vapor pressure is another one. We don't really talk about vapor pressure much in chemistry. We very, very well could, but we don't. The two colligative properties that we talk about are the ones that you saw in that gizmo from yesterday. They are boiling point and freezing point. Now, years ago, we used to make a big deal about talking about boiling point and freezing point in chemistry, and it kind of got left to the wayside. It was kind of moved to physical science. So just to reiterate what boiling point and freezing point are for chemists, right, for physicists too, really, boiling point is the temperature which liquid turns to gas. I prefer gas instead of vapor. You'll hear a lot of folks who like to use the term vapor. Not a big fan of that one. I prefer the term gas, right? So if you had this in 8th grade physical science or last year in physical science and they got a chance to talk about liquid to gas or liquid to vapor, either one. Believe it or not, that is the same temperature for a substance at a given pressure. So water boils at around 99.6 degrees Celsius here in Knoxville. Believe it or not, it's slightly below 100. It is exactly 100 degrees Celsius down at Myrtle Beach, down where you are at sea level, down next to the ocean. That boiling point is 100 degrees. But as you get above sea level, the boiling point changes. The boiling point can also change. It actually drops as you go up in elevation. But the boiling point can also change depending on if you add something to the water. Freezing point, then, is the temperature which liquid turns, let's erase that, turns to solid. Okay, so freezing point, you may have heard this before, but the temperature at which something freezes is also the temperature at which it melts. So if I see ice, I know it's at 0 degrees C if it's melting. Anytime that ice is melting, it's going to be at 0 degrees C. Now, the freezing point does not change that much based off of pressure. So ice melts in Knoxville around 0.01 degrees Celsius, and it melts at Myrtle Beach at about 0 degrees Celsius. Once it melts, you can get it as warm as you want, and once it freezes, you can get it as cold as you want. But if it's melting, in the process of melting or freezing, its temperature is 0 degrees C for water. That's for water. Others have different ones. If I add a solute If I add a solute to water, what's going to happen, right, is we have pure water, like this. Ooh, I'm moving my picture. Pure water, pure H to the acyl, and I add something like sodium chloride. Because I like my water salty, just like I like my YouTube stars. They gotta be salty. So you're going to take that, you're going to add them together. What's going to happen inside that water, right, is the solute's going to disperse into it, and it's going to break apart into its constituent parts. And then what's going to really happen, what's going to be really weird, is if we zoom in on one of these, what we're going to see is inside there, there'll be a little particle, and it's surrounded by water. Because that water is surrounding that particle, right, just like we talked about before, it's going to be attracted to that particle, and it's going to they're all going to kind of stick together a little bit harder. So what we're going to see, the colligative property here, is we see boiling point goes up. So because those water molecules stick together a little bit better, they don't want to boil, they don't want to go into gas, and we see the temperature, the energy it requires to do that temperature has to go higher and higher. Freezing point does the opposite. It becomes easier to stick those molecules together. And so we say boiling point undergoes elevation and freezing point undergoes depression. And there is a mathematical relationship there. The mathematical relationship is, for boiling point, the change in temperature at which something boils, aka delta TB, this is why we looked at delta T when we were doing this, is equal to, and people give these in lots of different orders, this is the order I prefer, all right, is KB, that is just a constant, times I, there's the Van Hoff factor, times molality. Here's the whole reason we've been doing molality right here. Molality is actually, it doesn't work for molarity. This only works for molality. What we see is that the molality of the solution is what determines the elevation in temperature. Isn't that weird? Isn't that weird? For freezing point, it's basically the same equation, just now we have a different delta T. It's delta TF because it's freezing, equals KF, which is just a different constant. The Van Hoff factor is still going to be I, and the molality is still going to be there. Isn't that weird? For water, the KB is 0.513 degrees C per moles. And for freezing, it's 1.8, either 8.1 or 8.2. Most people I know use 8.2 degrees C per mole. Some people, actually, I take that back. I'm sorry, it's not 8.2, it's 8.6. It's a different even number. There we go. KB is 1.2 or 1.3. KF is 1.86. There it is in my brain. All right. Tomorrow we're going to do some practice with these. We're going to do some math with these. But right now what I want to do is I want to talk about that Van Hoff factor, right? Why is it that sucrose has a Van Hoff factor? Let's go with I. The I of sucrose is equal to 1. But the I of NaCl is equal to 2. What the fudge? Why? Well, when you put sucrose in solution, it looks like sucrose. There's only one thing. But when you put NaCl, because this is an ionic compound, see how it's coming back? That ionic compound, remember, breaks into two things. It's going to make some Na pluses and some Cl minuses. Minus ones and plus ones. We'll put those on there. Can you imagine then when we look at ICaCl2, what does it form? Question mark. Well, we're going to get a Ca, and we're going to get 2 Cls. 1 calcium ion, and 2 chlorine ions. So this one has a Van Hoff factor of 3. Isn't that something? And that really changes its properties. This, by the way, is why calcium chloride, if you spread out salt on your sidewalk to try and get it to melt a little better, calcium chloride is what's preferred. It has a higher Van Hoff factor, and it's just as harmless as sodium chloride. More math on this tomorrow.